All right. Well, welcome everyone to our weekly Wednesday webinar series. You might be familiar with manual JDS, which is how you properly size your heating and cooling equipment and ducts to ensure good performance out of your system. But, whenever you're building new or doing a home upgrade, it's important to size your system properly, ideally using a blower door test to get air leakage for existing homes and including that test data in the sizing. Train trace is used for sizing on much of the larger multifamily apartments and buildings, mixed use within the same manner. These programs, Train Trace, Manual J8, Manual D, they're all used in Energy Star for the Inflation Reduction Act tax credits and certifications, and they're usually referenced and required in most of the residential green building certification programs. However, when it comes to the shift towards air source heat pumps, especially when they're not dual fuel or backed up with electric resistance systems, and more importantly, when they're in cold climates, you may need additional support to ensure you get the design and setup of these systems correct. Thus, that is why I'm super excited today to be talking about this particular topic. Now, before we get started, I wanted to let you know about our upcoming Certified Green Home Professional training. It'll go live in Grand Rapids, Michigan, and there's also a virtual attendance opportunity for you to call in. It's being held on September 30th from 8 a.m. to 5 p.m. You can learn more and sign up at greenhomeinstitute.org, CGHP 930. And support from the Green Home Institute comes from our sponsors, Build Equinox, now featuring the Serve 2 and Serve 1000 specifically for schools. These devices are energy recovery ventilators that keep air coming, but have been integrated with heat pumps to ensure maximum comfort. They're also demand-controlled smart ventilation, which detects poor air quality and only ventilates as needed, saving energy and reducing overventilation. Learn more about Serve 2 and Serve 1000 at buildequinox.com. All right, well, welcome everyone to Introduction to Heat Pump Sizing with the new Manual H. This session is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator. My name is Brett Little, and I am the education manager here on our small but mighty team of 3. This course is approved for multiple continuing education units, including our Certified Green Home Professional designation in 2 pillars, energy and health. AIA Health, Welfare, and Safety make it applicable to your state-based design or contractor license. And you can check for the Passive House 5-digit code for your Certified Passive House Consultant designation if you need that. It'll also be listed on your certificate at the end of the session. So with that, I am thrilled to invite back our speaker today, Ed Janowak from ACCA. Ed's been on the show now. I think this is your second time on our shows. So it's great to have you back out here, Ed, and I appreciate your time. Ed's also going to talk a little bit briefly about a giveaway that we're doing to GHI members who attend this session as well. So Ed, welcome. Please take it away.
Well, thanks so much for having me. This is a topic that I thoroughly enjoy. So it's a lot easier to talk about stuff that you like in comparison to there's times I talk about stuff that I'm not that fond of. That doesn't happen very often, but once in a while it does. All right, let me hit the share thing, pretending I actually know what I'm doing. And sometimes I do, believe it or not. Sometimes I don't. And whoever's crying right now, I appreciate that. Because that's the way it's supposed to be. All right. I am sharing, correct?
Yeah, yep. Just share your slide and then you'll be good.
Yep. There it is. You're seeing my home, or not my home screen, my introduction slide, correct?
Yep.
All right. Well, good. This is where I start off the beginning of the session with the hard part's over. More times than not, I am getting in a car and doing a couple hours of windshield time, or what happens even more frequently at times, driving to the airport and getting on an airplane. And my biggest concern is that everything works. the actual content I'm familiar with. And as I already said, it's stuff I like talking about. So with that said, we're actually going to get started. I do want to point out something that was kind of funny. Brett had sent me a mock-up of what we were going to use for this opening screen here. And that I think that is the picture that I still have on LinkedIn, which I still look like that. I just look a lot older. And the weird part is that's only like 5 years ago. So it's kind of, I'm lying. It's like 10 years ago, but I think it's pretty funny. Thank you. Whoever's hitting the laughy stuff, you're keeping me motivated. So, and it's not even really that I need all that much motivation. All right. On the previous screen, we saw a picture of Manual H as it looks today. And I do want to set the table a little bit when it comes to Manual H. Manual H is one of our manuals that is in process, is a good way to put it. The current version is literally from 1984, and it really brings joy to my heart when I say that you can look in stuff, and the majority of it was actually authored in 68. What's in that book from 68 and current, or is as current today as it was back then, I would say there's maybe 5% of the stuff that needs to be changed. There's definitely some updating that needs to be done, but a heat pump is a heat pump. It moves heat. It's the way these things work. So I've been a big advocate of heat pumps for a long time, and I can get real, I don't know, I could spend the hour just talking about my history of heat pumps, but I'm a fan. I'll leave it that way. The screen cover that is on your screen right now is the Manual H that sat on my desk at one of the places I worked for 15 years, because there was always a time that you could go reference what was in the guidance in this book that would always help you. And as I said, it's still relevant today. The current version of Manual H has 5 sections that we're going to kind of look at 2. And when Brett originally invited me to do this, what I had in my mind was completely different than what I think he had in his mind. So I had something already prepared, and then when he sent me the screenshot of what it was titled, I was like, well, that's not what I was going to do. But I actually think what he was asking for is much more relevant. So it guided me to a curriculum, if you will. I'm trying to sound like I'm smart. I'm not. I'm trying to put something together that I think people are relevant. But at the same time, there's fundamentals that's in this book that I can't ignore. And I'd like to think that people are happy to see them. All right, what is a heat pump? And it is the same technology that you would see in an air conditioner, that you would see in a domestic refrigerator. We're using the vapor compression cycle to boil and condense a refrigerant. And in the heat pump side of things, let me see if I can do this seamlessly. Yeah, that was pretty seamless. If it's summertime, we're going to take the heat that we're absorbing from the house and reject it outside. Pretty simple. If you're like a cool person, you stick your hand over the outdoor unit and go, yeah, that baby's working, because you can feel the heat. I don't know if it's exactly the same in the wintertime, but if you're accustomed to it, you can feel the coldness that's taken place when we're using the system to extract heat from outside. And that is one of the biggest misnomers when it comes to heat pumps. And that is the simple idea that there is a lot of heat outside, even during the temperatures that we would consider cold. Hold that thought. I'm going to go into more detail with that as we move forward. All right, air to air. There's different kinds of heat pumps, and I'm going to limit it to 4 right here. If you really want to drill down, you could tell me there's a bunch more, but for right now, we're going to talk about what I'm going to consider the most common and the up-and-comer, and you'll get what I mean by that in just a second. So different kinds of heat pumps, air to air, whether it's a unitary split like you see in this photograph here, or you're looking at something different as far as like a mini split or ducted mini or something along those lines. But air to air, that means that we're absorbing heat, we're rejecting heat to the outside air, and then we're absorbing heat from inside or rejecting heat to inside, air to air. Water to air. Water to air is a pretty common thing if you're familiar with the term geothermal. And this one right here is a pretty cool animation that I lifted from somewhere where it's showing this is a pond loop. Now I'm getting into subsections of stuff, but this is where they took the loop and threw it in the water. And that's where it's absorbing or rejecting heat to. Geothermal's a good way to do it. And this is where I show my love for the geothermal. I have two in my house. I've had geothermal in houses that I lived in since 1990. So as I said, I'm not just saying I'm a fan of them. I can prove it with what's in my own home. Next is air to water. And air to water is a type of system that's gaining a lot more popularity. If you've ever heard the term monoblock, it's kind of new to me. I was at AHR or ASHRAE this past year, and there was 3 different manufacturers that had them on the show floor, as in they're being put into production. Buddy of mine and have had this conversation that we were in a class 20 years ago, and the presenter talked about this is the future, air to water systems. And it's even more so prevalent because if you look in the not so distant future, we're going to start seeing the natural refrigerants take precedent over what we're currently using. And what I mean by that, the propane and the butane. You can put a piece of equipment outside that holds 3 or 4 pounds of propane in it used as a refrigerant, and you can make chilled or hot water. And then we're going to have a pump and we're going to put that hot water into the house, and that's going to be the medium to heat and cool the structure. Gets rid of a lot of potential problems that we already have and maybe some future ones. So watch out for that. And then last but certainly not least, during my years as an active contractor, water to water geothermal systems was one of our favorite systems to sell. And what is everybody's favorite system to sell? The one you make the most money on. We made the most money on them, but we could do everything. We could make air conditioning, and we could vary our indoor coil temperature. We could do radiant and put it in the floor or in the wall or in the ceiling, whereas in the photo on your screen right now, it's a radiant panel. A really nice way to heat a space. We got to remember that heat pumps do not generate heat, they move it. And that medium that we take that heat from or to is what we just discussed, whether it's going to be a pond loop, outside air, probably the most common, but there's different ways of doing it. But predominantly, we're moving heat, we're not generating it. This is one of my favorite explanations, and this is directly out of Manual H, and it's talking about heat extraction. This is the world we live in. I mean, realistically, we're not using a lot of heat at 60, but let's take it down to 50 or 40. That's where we're definitely heating houses. And depending on your location in the country, you're probably going to come down to about here. There's a lot of heat in that air. Is there enough heat to heat the structure? Maybe, maybe not. But if we compare it to how much heat is in air or could be in air, we see that that scale, that useful scale for extracting heat for the purpose of heating a home, goes all the way down to minus 460 degrees. So the actual scale that we utilize is small. So a way to sum that up is there's still a lot of heat available for us to use, even when it's what we call cold out. This next one, and this will give you a little bit of a insight where Manual H just explains concepts. I have every intention of doing this class for folks like you, where you might already be very well versed in this topic. And then there's a chance you might not be. So as this class goes from a 1-hour format to a 2-hour format, all the way up to a multi-day format, we can address people that are being introduced to maybe the first time, but also get into the heavy part of it. So we're going to see a little bit of a mixture of both as far as that goes today. In this one right here, it's just showing the, oh, I almost said betterness, and I'm making up a word. What makes a ground source system superior? The ground source, like whoever's hitting that smiley face, man, thank you so much. My house is a perfect example of this chart. And I have what they call pump and dump geothermals. It's open loop. The water that comes into my house for the heating and cooling aspect of it is 55 degrees. Doesn't go up a full degree or down a full degree 365 days a year. So if you were to look at the medium, right, the water or the source that's going to provide my heat pump the ability to suck heat out of it, it remains constant. And if you really want to get into it, my line would be further up here. But if we're dealing with an air source piece of equipment, as the temperature outside goes down, right, that's this column right here, we see that our system's ability to move that heat or deliver heat to the structure, it goes down simultaneously. I'm going to say very fundamental explanation of how a heat pump works, air source versus ground source. The next one is integrated capacity. And Manual H gets in explaining that when you have an air source piece of equipment and you have the ability to take the air outside down below dew point, we're eventually going to hit a crossroad where we're going to get condensation on that outdoor unit, and then it's going to start to frost. It has to. It's physics. It's psychrometrics. It's how it works. And we can see that if we happen to be in a completely dry environment, well, the heat pump can absorb a little bit of heat. But I'm not going to say it's impossible, but if you go to Denver or someplace in a very dry climate, those machines may or may not, chances are may not ever go through defrost cycles. And I'm wondering right now as I say that, that's why may or may not, I won't say it's going to work this way because I don't want anybody throwing stuff at me because they live in Denver and they had freeze-up problems last year. Coefficient of performance. Again, it's something to get people to have a fundamental understanding of how these things work. Coefficients of performance is how much it does for how much power we consume. And to use a very simple analogy, a piece of electric baseboard, you put 1 watt of heat in, you get 1 watt of heat out. It's that simple, dollar in, dollar out. When we're dealing with heat pumps, the best heat pumps I've ever installed in my life were up in the neighborhood of 4.5, almost 5 to 1 with the water-to-water systems. $1 in gives you $5 worth of heat out. It's very simple for a system like that to be the winner when it comes to what's going to be the most cost effective when you operate it to condition a home. So when you understand that the COP, when it's warmer out, when we don't need as much heat on an air source piece of equipment is good, we see that COP drops. But it's inherent how systems work. And if you really want to, this is kind of tongue in cheek, but it is reality. Heat pumps and air conditioners are stupid because they do less when we need it more. But I don't have the ability to break the laws of physics. So that's just simply how they work. And this is a bigger shot of what we saw in the bottom right with the COP thing. This is always fun. This was, and this is something I've been doing for 20 years. I have a gang in the classroom, and I have this is bad, but I can't help myself. I have a good knack for when I have that person who wants to show off everything they know to everybody, and I want to ground them a little bit. I would always ask the question, does a heat pump work harder when it's really cold out or when it's 55 degrees? And the definition of harder is it consumes more power. It's just like asking, is wet air lighter or heavier, right? If you add humidity, air actually becomes lighter. And without getting into the psychrometric side of it, I'll simply point out where the clouds live, right? They're up in the air because wet air is lighter. When we talk about things like this being, when does a heat pump work harder? It actually works harder the warmer it is out, because if you look on the right side, as it gets warmer out, we're going to use more power because it's simply moving more heat. Is it going to run longer down here? Absolutely. But we already defined that working harder is not running more, it's consuming more power. So again, this is pretty straight up fundamentals of how does a heat pump function. Sizing conditions. And let me see, this is what you were here for. How am I doing? Oh, I'm pretty much on time. That's kind of cool. So when I talk about manual H and it being very current, this is a spot where I don't know if this was thought of yet. Because if you go back to and I'm fairly certain, I'll argue with you, and I don't have anything to back it up, but I just like to argue. Manual H, this section, I'm fairly certain came from the 1968 part, and they wrote about a whole bunch of stuff that has to do with heat-only applications, which I'm fairly well versed in these, and it's something I'm not really that familiar with. When we start to get into I'm talking air to air. You get into monoblocks and stuff, sure. But when we're talking air to air, heat only applications, I'm going to say they're rare. All right. Instead of saying they don't exist, I'm going to say they're rare. This way I don't have to argue with anybody. But they would be correct if they said maybe they do exist. I don't want to follow anything that's in the current manual H when it comes to sizing. What I want to do is go down to this guy right here. I want to follow manual S. I am a giant supporter. Maybe S in manual S stands for supporter. It is what we're supposed to do. And I'm going to spend the next 10 or 15 minutes convincing you why we want to follow the guidance in manual S. Following the guidance in manual S, it does a lot more than just what I'm going to talk about, it being manual S. But manual S is written, when whether we're talking about, I think it's on the next slide, whether we're talking about the OG, right, from 2004, whether we're talking about the 14 version of manual S, or the most recent version right there, the 2003 version of manual S that recently came out. And I'm adding this word, but it is imploring you, if you live in a climate where there is moisture, to make sure that you're taking care of that moisture in the summertime. That's if I want to chalk manual S up to one thought, that's it. It's got some other good guidance to show you how to do stuff or recommend how you do stuff that I helped write it, so I'm kind of in agreement with it. But at the same time, it's got some stuff in it that is so important that just gets lost. So when we talk about the whole heat pump electrification and all that, I'm 100% for it, right? But I'm for it done right. And there's some stuff in there where I think we got to do everything we can to fend off the great heat pump revolt of 2028, because there's going to be some unhappy people out there if some of the things that are happening continue to happen. And thank you for the support on that. I think there are people that are very well intentioned. They don't get it. I've been fortunate enough to speak in front of some pretty big groups, and I know part of it is the reason they asked me to talk about it is because I can make people laugh instead of maybe people just getting pissed off, or excuse me, getting angry. But it's one of those things that I find it weird when I say I catch myself getting passionate about this stuff, and it's not something you're supposed to get passionate about, but I think it's a big deal. A big part of everything that I do with the design series and getting people to do proper installs, or at least the design behind proper installs, is I want everybody to sleep good at night. It makes me sleep better at night knowing that I'm helping people with this, and it's math and it's physics and it's science, and I don't have to make stuff up. I can just say, do this. It's in your best interest. So I'm going to let this one sit long enough for everybody to grab their phone. Take a shot of that, and it'll give you access to it. It being, ACCA has changed the way it is going to do all of its manuals going forward. the ICC manuals, a bunch of the ASHRAE stuff, you can go get not a downloadable copy that you can print out or manipulate in other ways, but the normative section. ACCA manuals have normative and informative. Normative is the must and shall stuff that you'll see referenced in code. That is available to you right now. You can't do any, it's read only. That's the phrase I was looking for. So it's available to you. And the manual asks, like we are used to seeing books, hopefully by the end of the year it'll be out. So it'll be the normative section, and then it'll also have the guide which walks us through everything. So that's on the horizon, but this is something that's nice because I've run into some issues periodically where people are like, well, it's beat, I shouldn't have to pay for this. And they're not wrong, but this was a good move that we've taken. And I don't know, maybe I criticize where I work to people when I shouldn't, but I'm going to take a little credit on why you can get a copy right there. All right, back to fundamentals. This little guy is going to show us a psychrometric chart. If you've seen a psychrometric chart before, it's not that hard. It can be a little heavy, but real simple. 75, and it's funny, I'm pointing at my screen like you can see me. There's 75 degrees dry bulb. That's our target temperature inside the house in the summertime. What we got right here is 50% RH, right? There are design criteria for our target inside the house. One of the reasons that is our number, if we draw a line horizontally, this tells us the dew point is 55 degrees in the house. 55-degree dew point. I got a 75-degree temperature I'm going to maintain. I got 75-degree return air. The magic number for air conditioning has always been 20 degrees. If I can do something where the air coming out of the top of the evaporator is 55 degrees, by the time it touches a metal surface, it's going to be 55.1 or greater. I can have uninsulated duct systems that don't sweat. When you see sweaty ductwork inside the conditioned space, somebody's breaking the rules. Either the house is too humid or something else is going on, but that's the backstory, if you will, behind it. I size to that temperature to ensure I can maintain that set of conditions on a design day. I live in the mid-Atlantic. 90 degrees is my design. On a 90-degree day, I am going to tell the people with 100% certainty I'm going to be able to maintain those conditions. When it gets hotter out, is there a chance I could lose ground? Yes. But I make that concession because when it's 80 degrees in gray, I still have a very good opportunity with my system to maintain humidity. And bottom line, I care more about humidity on a part load day than I do on a design day. I'm blunt, I don't care. This goes back to the predictability of this whole thing. You have to manage people's expectations on how it's going to work. And when they tell you, I want something bigger, you have to bluntly ask them, do you want a house that's more humid the majority of the time? That's what it comes down to. Now, are there paths where you can make it a little bit colder if you just have that customer? Yes. And that path includes ancillary dehumidification. You have to address it. You cannot make a house more comfortable with a system that's larger than necessary. It's that simple. And if I got to explain that to one person at a time for the next however many years that I work, I'm willing to do it. Because I have people that I have completely changed their mind, and literally they will make comments about how it really has reduced a lot of the issues that they have. It's I'm going to say it's that simple. So next screen is expanded performance data. Part of the whole Manual S process is you got to understand this stuff. It's not you do a load calc and it says 2.2 tons and you buy a 2.5 ton unit. That's not how it works. You look at the manufacturer's expanded performance data, and in this first box up here, we see it's 850 CFM for a 2-ton system, and I've got 75 degrees, at a 62-degree wet bulb. We saw it on the previous slide. That's 75 degrees at 50% RH. And we're in the eastern tip of Long Island where the design temperature is 85. And you don't augment those temperatures. You use what is listed in Manual J for those locations. It's doing, and I'm doing this thing where I'm pointing at my screen again with my finger. This combo up here, this combo of equipment is doing 23,400 BTUs of total, and it's doing 19,000 BTUs of sensible. We do a little bit of math, and we determine that it's doing 4,400 BTUs of latent. This is the precision. This is the actual math behind doing this properly. And I'm not going to go into the same detail moving forward, but I'm going to say there's 800 CFM. There's your magic 400 CFM per ton. And then we see it again with the lower airflow. And we see total capacity drops, sensible capacity drops, latent capacity increases as we slow that fan down. That is how an air conditioning system works. And our goal is to find a piece of equipment that meets the sensible, meets the latent, doesn't exceed the total by a percentage that's going to be listed in Manual S. The first 3 or 4 times you do this, you want to put your fist through the wall. But after you do it 6 or 7 times, you got your partner next to you that's doing the same thing. You're like, hey, what's your sensible heat ratio? You know, it's just another step in doing proper design, and it's math. There's nothing that's crazy hard about it. Prove it. That's a term that we use quite a bit lately here at ACCA with commissioning systems and all that. It's all part of the process. If I tell somebody something's going to do something, I want to know it's going to do it. And it goes back to that whole predictability thing and all that. Sensible heat factor. You might know it as sensible heat ratio. Sensible heat ratio, whether it's equipment or it's a structure. If you take the sensible and divide it by the total, sensible gain divided by the total gain, that gives us a sensible heat factor, right? That's tells us what percentage of our gain is sensible. What has happened over the last couple of years, a couple of manufacturers have saw the confusion between talking about sensible heat ratio of the equipment and sensible heat ratio of the house. So a couple of the manufacturers started calling the sensible heat ratio of the equipment sensible heat factor. Sensible heat ratio for the structure still remains. So moving forward, I try and incorporate the sensible heat factor. So here we go. This is more fundamental stuff. This is Ed's system right here, and Ed's system can do whatever Ed wants to, and I don't have to annoy any particular manufacturer. But we're going to talk about sensible heat factor. I got a 10K unit. It doesn't exist. You can buy a 9 or a 12, but it's mine, so I can do whatever I want. And when I'm doing whatever I want, I can make it 10K. And if you've figured it out yet, the reason it's 10K is because I can do the math without using the calculator on my phone. 10,000 BTUs of nominal capacity. It's operating at a sensible heat factor of 0.75. And I could determine that from my expanded performance data. But again, this is an explanation of how these machines use some of their capacity to drop the temperature of the air and some of their capacity to pull the water out of the air. It's doing 7,500 BTUs of sensible capacity because it's 10K times 0.75. And then the remainder, the 2,500 BTUs, these are these guys, right? It's 2.5 pounds of water. Oof, don't get me started on that. I'll tell you how long it takes to fill up this thing and how many BTUs it is. Because it's all math, right? It's all kind of straightforward. Manipulate airflow that sensible heat factor changes. What I mean by that, bigger airflow is defined as greater than 400 CFM per ton. Smaller airflow is defined as airflow less than 400 CFM per ton. So if you have a really good house, high efficiency house, it would benefit from bigger airflow, and bigger airflow might be your goal. But bigger airflow in a system that has a higher sensible heat factor is not what you want to throw in a basement, right? Brett and I were talking a little bit about some of the craziness which exists in our world right now, and it's because people don't understand these basic fundamentals. So if we manipulate the airflow, more air gives us a higher sensible heat factor, and we'll be more efficient, right? And that's the majority, not all, but the majority of these mini splits are super efficient, and they run sensible heat factors. And this is EER, not SEER we're talking about here, but at the end of the day, they're the same. This is theoretical, right? This is the magic 400 CFM per ton, 0.75 sensible heat factor. In this one, it's my dream system, right? It's pulling out a lot of water. We look over here in our sensible, let's see, no, this is our total capacity is less than its nominal rating. That sensible heat factor is shrinking down, right? And that gives us the ability to do all this glorious work right here. And we see that more latent, our ability to drop the temperature of the air, right? The amount of it has been reduced and it's less efficient. That's the penalty, if you will. When we have a machine that's really good at pulling water out of the air, its efficiency goes down, right? This is the hopeful system that we see in the field. This is the type of deal that could potentially work in a basement. This goes in a house that's leaky. Next, we got this guy, and it's hardly got any water coming out. When I spoke to this in the very beginning, there's a bunch of systems out there. Again, it's 10K, just like the previous two. It's doing a little bit more total capacity. It has the ability to move a lot of heat, but the majority of the heat that it's moving is sensible. I mean, they've all been sensible, but it's even more so. We have an even higher sensible heat factor, and it is more efficient. But if you're in that house that's a little bit leaky or a lot of bit leaky, having a higher sensible heat factor in your equipment is not ideal. It's just how it is. That's reality. My friend Alex Meany, I saw him at a conference a bunch of years ago, and he was goofing with the microphone. He kept saying, "Look it up, look it up." And that's what this stuff comes down to. You can't pick a 10K, a 9K, a 12K system. You have to go in and look at its performance data and know what it's going to do, and then make your decision. Yes, that'll do what I'm trying to achieve. No, it won't. That's how it works. Can I get somebody who's been doing the thumbs up or the thumbs down? Are you getting the lawnmowers going by right now? Or is it not so bad?
Are you hearing something on your?
No, I got lawnmowers going by.
Oh, I don't hear a thing, and we're good. So go ahead.
Good. It's where I feel a little bit out of place. I'm used to sitting in my basement with all this stuff. I'm in a hotel room doing this, so it's I don't know. I wouldn't say it's a big adventure, but it's something I'm not used to doing. Anyway, manual S, and what I'm quoting right now comes from the 2014 version. It says, and I'm making it a little bit, what's the word I'm looking for? Dumbed down, if you will, right now. And what it's giving me is 15, 20, and 30% oversizing, right? Meet the sensible. Remember that expanded performance data. Find a piece of equipment that meets that sensible, meets the latent. Don't exceed the total gain by 15% if it's a single stage compressor, 20% if it's two stage, 30% if it's some kind of variable refrigerant flow type of system. The new manual S pretty much stays in line with that. It's got some caveats. What has happened in the new manual S is it's really trying hard to give people the ability to heat 100% with a heat pump, but at the exact same time, it's holding your feet to the fire so that you're still maintaining that cooling, that latent cooling that's required so that we don't experience angry people, right? We don't want to raise the dew point in the house. And when we put oversized air conditioning equipment, that is the reality as to what happens. There is going to be 6 different classifications for this. And I am going to prepare you right now. If we're doing this for real in a classroom setting, what I'm going to go through in the next 14 minutes is 3 hours. There's two ways to do this. To give you a brief overview, tell you to go read it for yourself and apply it to some of your systems, and you'll see what's going to work. I can't get into that much detail and explain it completely because there just simply isn't enough time. And to be blunt about it, I don't have all of these different sizing processes memorized for this like I did in the past. I don't have the repetition with it. I know how to apply it. I shouldn't even say this, but I'm going to say it anyway. I agree with most of it. I wouldn't say I don't agree with it, but there's some caveats in there, and we'll just leave it at that. So let's go through them. And again, we're going to go through them pretty quick, but it'll give you some guidance. First thing, Manual S has some really cool of these box charts or flow charts. As you start to figure this stuff out, they can definitely be your friend until you get to where you want to be. This is it. These are the tables that are the heart of this book. If we have single speed equipment, and this is air conditioning, and this is standard sizing. Standard sizing, whether it's an air conditioner or a heat pump, that's my thing to do. I don't like sizing to heating. I like sizing to the air conditioning requirement. And if I'm in a heating climate, I'm going to put electric resistance heat in to make up for that 10%. And I made that number up, but for that small amount of heat that I need, that supplementary heat, I'm doing it with electric resistance. And I'm not trying to jump through hoops with a lot of these other processes do. Now, if you're in a market where they say, no, I don't want any electric resistance heat. I've recently been in conversations with people that I would have told them they were completely crazy, but now I'm like, yeah, you're right. If peak demand being switched from a cooling demand to a heating demand, because we see in the not so distant future that they're going to put in hundreds of thousands, if not millions of pieces of equipment, it's got to be done. There's no arguments there. They still might be a little bit crazy when they say the average person is going to go buy a 1,500-watt space heater for their house for those couple of days that they need it. I wish I had clientele over the years that would agree to stuff like that, but no, I get it, and I see its importance, so I'm going to share all this stuff with people as much as I can so they can potentially do it. Okay, rant over. Air to air, water to air, single speed. If it's under 24K, this is something that the goalposts got moved. It used to be 15%, but if you're under 24K, a little more wiggle room where you can go up to 20% over for a single speed. The 125 for a two speed, that used to be 120%, little more wiggle room. That's the way it goes. Sensible, you got to meet 90% of your sensible gain. So when I said meet the sensible, meet the latent, when you're meeting your sensible, you really only have to meet 90%. Latent, you got to get rid of all the latent water on a design day, but sensible is at 90. That falls into, if I have my druthers, I would rather be slightly undersized than oversized, period. And I've been doing that for a very, very long time, and I'll tell you, I've been successful with it. And that was our two-speed. I got slow on the draw with the, oh, and there it is right there, that when I do the, what do you call it there? I love this, right? This is my favorite by far. That's the way I'm going to size stuff. And the same thing goes for when I'm doing dry climate stuff. That's how I'm going to do it. If you want to do something different, then that's why there's different guardrails. Dry sizing. If you are in a location where your manual J sensible heat ratio is greater than 0.95, and there's a picture there of the desert, because that's exactly what we're talking about right here. We're talking about desert type climates. Is there water to be pulled out of that house? Yeah. Is it going to happen on a design day? Probably not. So I still want to be ready to deal with water, but not nearly as concerned with it. And that's for both single and two-stage equipment. The next category two-speed heat pump sizing where we have that J sensible heat ratio 0.95 or greater, or right, the 0.95 or greater, that is naturally occurring. Active dehumidification, we can make that occur. So if you want to put ancillary or active dehumidification in, I think it is a better mousetrap if you're going to do it and follow the rules as per Manual S. But you have to follow the rules. You have to actually do it, right? I love ancillary dehumidification because it takes away all of my anxiety when it's 80 degrees and gray. I'm relying on a piece of equipment that I literally am hoping runs enough. But when I have ancillary dehumidification, that's the holy grail. So if you have customers that are super finicky and they want it a little bit colder in their house, it's achievable, right? And you can follow the rules. What better outcome is there than following the rules? Next, variable capacity equipment and simplified. I've already said it once. If I have my druthers simplified, I want to do everything, if possible, simplified. Can't always do it, but if I can do it, I will. So this is going to be my go-to, even with the VRV. There's a lot of people out there that are into the VRV and they want to go much bigger. And if you want to go much bigger, again, just follow the rules. And here we go. Again, simplified heat pumps. We have some rules. If you're doing simplified heat pump, you got to heat it. You got to heat it, right? Is there allowance for one rack of resistance heat if you want it? Sure. But as the rules are applied, you got to heat it. And the minimum compressor heating size factor right here is 0.8. And this is where you're going to start taking your favorite combos and comparing it to these rules. And you're going to find pieces of equipment that fall right into it and life is good. And you're going to find some that you're going to be rolling your eyes and it's like it's off by this much. But these guardrails are in place to ensure that that dew point doesn't increase on those less, well, even on a design day, but more so on a less than design day. So we've got simplified. We did simplified cooling only. That was simplified heat pump. Next, we have our advanced heat pump. And with our advanced heat pump, our minimum compressor cooling size factor has to be less than 80%. We have to 100% meet the latent like we did before. We got 100% meet the heating requirement, and our minimum compressor heating size factor has to be less than 80%. Again, it's another set of guardrails so that we don't put a piece of equipment in that's larger than necessary. So I wouldn't be surprised if I said trying to stay away from larger than necessary a dozen times today. And if I haven't, I'm going to say we don't want something that's larger than necessary because, again, a bigger system doesn't dehumidify as well. And that's why we have to stay within these factors. And then last but not least, we have our advanced dry. And advanced dry is going to be you're in the desert again, or you're putting in the active dehumidification. If I had a guess, it's strictly a guess, I'm going to say this last one is probably going to be the most common scenario that we see for the people that want to go all heat pump, but we have a 2-to-1 ratio. And a 2-to-1 ratio is going to be, I need a 2-ton air conditioner and a 4-ton heat pump. Now, I know I just said you don't size stuff that way, but a 2-to-1 ratio, if you want to heat completely with a heat pump, I think you're going to have to utilize active dehumidification. So it's one of those things that is necessary. And for me, I'd rather go back to my favorite where I use electric resistance for backup, but I'm going to say the advanced dry is my second favorite if I have to just pick two. Manual S, since its inception, has been telling us that when we go to select equipment, more often than not, you're going to have excess latent capacity. and half of that excess latent capacity can be applied to the sensible capacity for the purpose of meeting our loss and gains, or really our gains. Getting back to Manual H itself, it has guidance on the design balance point. The design balance point, we can manually build a graph. And I think I don't have it bigger yet. Let me go back. I'll show it to you a little bit bigger, but this is our heat loss. And this is our heat pump's capacity. And where these two intersect, it's telling us that we have a thermal balance point of 35 degrees. So between this intersection and this intersection, that's going to be the requirement for supplementary heat. Don't do that. Go download the Manual S speed sheet for free. You put in your heating capacity. You can do the whole thing if your manufacturer supplies it. At a minimum, they're going to supply capacity at 47 and 17, and it's going to tell us our balance point. These numbers that are on this are the same numbers that were in the previous slide, so it's not a shock that the numbers come out the same for what our balance point is right there. And that's an example of our heating performance data. These are the two 47 and 17 that every manufacturer is required to list, and that's going to be for the HSPF rating. But the manufacturers that I'm familiar with are going to give you a whole bunch of different heating temperatures, and you can make that line more precise. Does it really matter at the end of the day? No, I'd use the speed sheet. And there it is, blown up a little bit so you can see it. This is our heat loss. All right, we're going from 0 up to 25K in heat. And this is our heat pump's capacity at 47. And then down here at 17, it's a nice level line. All right, actual operating balance point. This is my swan song in some respect. I've heard a lot of criticism about Manual J, specifically in the heating, not being very accurate. And it is, period. But what's blown up at the bottom in the bullet point, it says Manual J has inherent and appropriate factor of safety. It must. Unless you have a way to take the sun out of the equation, Manual J is going to produce numbers that are explained in the first bullet point, and I'm going to read it verbatim. When the heat pump is operating in the field, the actual balance point is seldom equal to the theoretical design balance point. It's because Manual J is going to ignore the solar gain on the structure because there isn't a reliable, and it's not just Manual J, you can go through any ASHRAE process right now. There isn't a reliable way to estimate the sun's effect on the structure and ensure that we're going to maintain temperature on a design day. That's the way it works. If you want to do something where you're using some other type of process that is not recognized by ACCA because it doesn't follow the guidance of Manual J, use two different things to come up with a number, perfect. But Manual J does a very good job at what Manual J is supposed to do. Don't get it confused with what you want it to do versus what it actually does. Supplemental heat. When we hit that balance point, until we get down to whatever our design temperature is, that will be known as supplemental heat. And how cool is this? The speed sheet does our supplemental heat for us, just like it did our balance point. So that's something that's super convenient for us. And then moving forward, that's what we're trying to get away from, right? We want to put enough heat in the house that we never get to the point where we got to start doing that. And again, I think the 1500 watt heater from the Walmart is a better choice than doing that, but I can see that being a potential issue. And I can't take credit for that photo. I saw it and I stole it and I laughed, and that's a good picture, but that's reality. All right, we have sizing limits for the resistance heat for supplemental heat only, and we're running out of time. So I'm going to say, if you're more interested in this, go look it up in the document that you were able to download from the RF code earlier. And then same goes for emergency heat sizing. There's limits, and I do a lot of stuff, or I used to do a lot of stuff in on the west coast of Florida, and you didn't do this. Everybody gets 5K because that's all they need. It's more important. You want to stage those heaters so they don't run more than they need to and that kind of stuff. But it's following the rules. Once you read through the rules and you realize what they're saying, it's fairly straightforward. And we did it. And we're going to have a couple minutes for some questions. Not a lot, but a couple. Do we have any questions? And I will switch to my last slide. If you want to get a hold of me somehow, that's me and my crew. That's what I try and do more than this, but I have to do this to support that. But if you're a Snapchat person, I'm very active on that, all that stuff. So.
Yeah, hey, thanks, Ed. Real quick before we get into those questions, just a reminder that yes, this session is being recorded. It'll be hosted up on our YouTube channel in the next couple days. You can go there then and check for it, or you can go subscribe now and you'll get an instant update when the session is.
I really like it when stuff's recorded, and at the end I realized that I didn't curse. So
I think you did good there. So
Paul,
yeah.
I already had somebody, Paul, connected with me on Snapchat. So
Great.
He'll be able to tell her. My stories are amazing. I'm away from home, so I take all the pictures in the airport and share all that goofy stuff. And anyway.
Yeah. Well, thanks for that, Ed. And real quick too, for those of you looking for your continuing ed, watching this in the future on the recording on demand, take your quiz with an 80% passing rate. For those of you here today, if you've been here for the entire CEU session approved time, fill that survey that pops up, put your AIA number in, and then check your spam over the next couple of days. Certs at gutenbergcerts.com. You will receive your continuing ed certificates. And as always, a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, over 350 members, and all of our sponsors, especially our top tier sponsor, Rheem, Build Equinox, Mitsubishi. They're all making heat pump technology to help heat and cool and decarbonize and be more sustainable. So, Ed, I really want to go back to that last thought real quick on Manual J, maybe to help clarify something. I have a heat pump. This is a personal issue, but I want to clarify it for everybody. I have a heat pump, and in the clearly sized for the winter, where I'm climate zone 5 up here in Michigan, very cold weather climate. You've got the sun beating on my house. There's like no shading, and there's a lot of times now where that thing really just can't get to the set point. And so I want to clarify what you just said. Did you say Manual J does not account for the sun? Because I would have thought it was the other way around, but help me understand that.
You're talking about summertime, correct?
Yeah. So you were talking about wintertime. Yeah.
And excellent question. Manual J does a spectacular job of being very, very close, or as close as it can, as long as our inputs are good, to giving us a number that coincides with reality. In the heating, it doesn't, because it can. So I'm glad you brought that up so I could clarify that. Summertime, it's a rock star.
Yeah.
Here's in it's 4-15. And if I actually got that right, there's something wrong with me. There is an image in Manual J, and it shows us it's a 3-ton house when it's cloudy. It is a 4-ton house when it's bright sun. That sun makes such a big difference on the structure that we have to model it, right? The load calc has to do it with bright sun, but our system theoretically and in reality is larger than necessary when it's cloudy. But how else are you going to address that? So there are, if you want to call them faults within these books, okay, I'm going to call them misunderstandings, and people have unrealistic expectations. I've done a whole presentation at a thing that I'm at, that I'm at right now, where I go on a rant for 15 minutes. More people understand how to use Manual J from using software than from reading what's in the manual. So They get used to this. This is what I want it to do. And they don't realize that the process has limitations.
Hmm.
But if you follow the rules of all the books, you'll, at the end of the day, I saw somebody asking about, are people okay with 75 degrees? And here's the deal. People don't have to keep their house 75 degrees. They can keep it cooler.
Right.
But when it's really, really hot out,
Hmm.
there's a shot they're not going to be able to maintain that 75 degrees or that 72 that they want. Let
Yeah.
them put it at 72 when they go to bed. When
Yeah.
the sun goes down,
Yeah.
the heat that's in the walls is going in the other direction. They're going to be able to maintain temperature. That being said, if you have houses that they're 80 degrees on a day where it's not a design temperature, there's something wrong with the system.
Hmm.
And I did a lot of work where I went out and looked at complaint houses because the utility was getting sued or the supply house was getting sued. All the systems ran, but they
Hmm.
were all the same problem. You find a gap in the ductwork and it would fail the watch test. You familiar
Hmm.
with the watch test?
No.
Your hand goes in the gap all the way up to your watch, so you're losing 25% of your capacity. That's copyrighted, might not be accurate, but it is. Low airflow, improper charge, systems not running the way they're supposed to.
Hmm.
And our industry, incorrectly, but they still, we have been taking care of systems, complaint systems with capacity, bigger unit, than fixing duct systems or fixing whatever's wrong.
Hmm. Hmm. Ed, I know you want to get to lunch. There's a lot of questions. Do you have time for a couple more here?
Yeah, I'll take three.
Yeah. Well, so there were a lot of discussions around, how this relates to variable speed or inverter driven. So just real quick, when someone says variable speed, when someone says inverter driven, as far as the heat pump, are we saying the same thing, or is
Yeah,
there a distinction? Okay.
variable refrigerant flow. And
Yeah.
I'm terrible at it too, because I'll call it VRV one time, I'll
Right.
call it inverter the next, and I'll call it the book is good about giving it one title, and
Mm,
that's the 30% part, and it's wherever it's uses the word variable refrigerant flow, they
yeah.
all fall into that.
Right. So then the question was, someone said, okay, you gave me a partial answer on what I was looking for that. They said, would you say the minimum compressor heating size factor takes precedence over the maximum when sizing for a heating? For example, if the former is 0.7, but the latter is 1.5, it's okay, taking into
What I'm saying
consideration.
is you're going to follow the guidance that doesn't oversize the air conditioning by the limit.
Yeah.
Oversizing the air conditioning is the hard stop. If you're going to oversize the air conditioning requirement, then
Mhm.
you got to find a different unit.
Yeah. You
And I
talked about,
also live in a glass tower because I don't get stuck with one manufacturer. I have access to everybody. So,
sure.
sorry, not sorry.
Yeah. Fair enough. And then so you mentioned this 2-to-1 ratio. They're asking what happens with the 3-to-1 ratio of heating to cooling.
You still got to follow the rules.
Yeah.
So, in a scenario like that, you got a 3-to-1. Uh, I'm going to put an appropriate size. Follow the rules so it's as appropriately sized as possible. I don't think I'm ever going to find a system that isn't going to rely on supplementary heat in one way or another.
Hmm. Hmm.
So dual fuel. I didn't even use that term today, but that would a perfect example of that would be a dual fuel.
Yeah, and I'd assume you were talking when you're talking about the electric resistance backup being in place, that would be synonymous with a dual fuel, right?
Yeah, I was trying
Just
to
have
stick
some.
to all electric, but when you throw 3-to-1 at me,
Yeah.
I got nothing. That's maybe you go to Walmart and get 4 of those 1,500-watt
Mm.
heaters and spread them around the house. But
Um, so considerations for SHF for refrigerant-based systems or hydronic ones. Any thoughts there? That's the
you
question.
got to look up what the manufacturer says they can do.
Mm.
Personally, what I have found is that if you look at expended performance data,
Hmm.
it's real life. If you look
Hmm.
at marketing brochures and they say they have a dehumidify mode, one of the dirty little secrets with the mini split stuff is there are manufacturers that have little lights that blink and they say that it's going into super dehumidify mode and it's got absolutely nothing inside of it that can regulate that.
Yeah.
It's
Yeah.
marketing. It's
Yeah.
I am gonna curse. It's bullshit. So you gotta bleep that one out.
All right. Well, yeah, we Ed, really appreciate your time and ACCA for having you out. Just as a reminder to everyone, we're going to do a drawing, a giveaway. So anyone who's a GHI member by midnight tonight, you're going to either get a chance to get the book or the class. Can you just what's going on in the
Yeah,
class?
we have a virtual class. It's the design series that I teach. They're 2.5 hour,
Yeah.
and the manual H one should be out by the end of the year. But
Okay.
I'm doing humidity, which is a fancy way to say psychrometrics. But when we call it psychrometrics, people were scared and wouldn't sign up. As soon as we called it humidity, we'd get 20 people in the class. We do J, S, and D.
Okay.
We have an airflow class. We have a bunch you can look at, and at your convenience, you can take it.
And if people go to ACCA.org, they can
Yep.
sign up and they can see the classes come up on a newsletter or something like
Yep.
that.
Yep. All that.
All right.
And here's
Uh,
something really trashy for me to do, but if anybody had any inkling on joining ACTA, and I'm not doing this for anything other than to save you $100, use code ED100 when you sign up, you get $100 off.
all right. There you go. There you have it. Check it out. Ed, Janwak, thank you so much for your time. Take care. Be well. We'll catch the rest of you next week. So
Yeah, get a hold of me next time you want to do something again. I'm always
yeah, we'll be in touch. So
I'll
take
try and be home.
care. All
Take
right.
care.
Bye.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.